In this example, we're considering again a first-order homogeneous system, and that means that our goal is to compute the eigenvalues and eigenvectors of the matrix A, which really defines the relationships in this system. Notice we also have, though, an initial condition that we'll need to satisfy, and again, if you think back to earlier examples, this will let us find C1, C2, and C3. We're going to have three solutions because it's a 3 by 3 matrix with three variables, and this is going to give us the ability to find those undetermined constants in the general solution that narrow it down to a particular solution. All right, so we know the process now. We're going to find the eigenvalues, and we get that by solving A minus Ri equals 0, with the determinant of that being the key ingredient. Vertical bars also indicate determinants, so let's just copy our matrix in here. Then the minus r times the identity matrix simply means that we put a negative r down the diagonal. And then we're ready to take the determinant. Now for a 3 by 3 matrix, the system I prefer to use myself is to extend this matrix by copying the first two columns over. And then we can do something like we did with the 2 by 2. So just literally copying over those first two columns. And then what we can do is take 3 products this way and 3 products this way, and we'll use positive combinations for the black lines and negative combinations for the red lines. I don't tend to dress up the actual solutions on paper with this, but this is just a mnemonic for the procedure. If we go down this first black line, we notice there's a 1 minus r, a minus r, and a 5 minus r. Next line, which we add, is 2 times 4 times 1 is 8. Third line, which we add, is negative 1 and negative 4 is plus 4. Then we follow these red lines up. So we're going to subtract 4 times negative r times negative 1, so that's r times 4. Then we're going to add, so we'll have the negative out front of this entire operation. Then we have negative 4 times 1 minus r. And we have 5 minus r times 2. And all of that is going to equal 0, so that the determinant of this 3 by 3 matrix gives us a 0 value. We'll do this incrementally. This is negative r plus r squared times 5 minus r plus 12 minus, and this time we'll do it term by term, minus 4r. This is plus 4, and then minus 4r's. Then this minus sign across the whole way is going to be minus 10 and plus 2r. All of that equals 0. Last but not least, we'll have an r cubed. We'll put it first because it's the biggest power. We'll have plus 5r squared. We will have minus r squared, plus r squared, double negative. And we'll have 5 times minus r, so minus 5r. For these terms down here, we have 12, 16, minus 10 is 6. And then we have negative 4 plus 2 is negative 6r's. Grouping again, r squareds, we've got 6r squareds. We have negative 11r's plus 6 equals 0. This part here, recall, is what we're going to call the characteristic polynomial, or equation if we include the other side. And as soon as we know what A is, as soon as we're given a matrix, there will be a characteristic polynomial. By the time we expand it out, we get a cubic if it's 3 by 3 and so on. Let's make our lives a little bit easier by flipping the signs everywhere, so it's not negative r cubed. And if we do that, it's a cubic, so there's no guaranteed way to solve this, but we do notice that r equals 1 satisfies this equation. We have 1 plus 11 is 12, minus 6 is minus 12, we end up with 0. And that means we should be able to factor our negative 1. All right. Then we can do our fill in the blanks kind of factoring. We have minus r squared already. We need minus 6, so we're going to need another minus 5 r's. We need 11 r's. By the time we're done, we'll have plus 5 of them, plus 6 of them, so that's actually the correct factorization there. And even better, that has a nice factorization as well, which is r minus 2 and r minus 3. And that gives us our eigenvalues are literally 1, 2, and 3 for our matrix A. Fantastic. Next step is to find the eigenvectors. For that, what we take is A minus Ri times some unknown vector equals the 0 vector. And we do this for each eigenvalue. So we might as well start with the easy one. Let's do r equals 1, and we build our matrix with the A minus Ri form. So we're going to subtract 1 down the diagonal. That gives us 0, 2, negative 1, 1, minus 1, 1, 4, minus 4, 4. That times 3 unknown coefficients is going to equal the 0 vector. So at this stage, what we can do is either row reduce further to simplify the equations, or work with what we have. What we have here is fairly simple, so let's just keep going with it. And we'll do it explicitly in terms of coefficients. We have negative 2 v2s minus a v3 is 0. So 2v2 is the same as v3, or v2 is a half v3. And remember, we get to pick one value ourselves, because any multiple of this is okay. So there's going to be some freedom to choose. But once we pick v3, let's pick a nice integer to make this work out. Let's pick 2. And that'll give us v2 is a half times 2, which is just 1. That's nice and quick. It gives us 2 of the values. We can then use the second equation here to tell us that v1 minus v2 plus v3 has to add up to 0. Those coefficients multiplied by the variables. v1 is the one we don't know, so it's positive v2 minus v3, and that positive v2 is 1, minus v3 is 2, and so we get negative 1. So all these combined give us our vector v, which is going to equal v1, v2, and v3. And that's our first eigenvector to go with our first eigenvalue. To find the next eigenvector, we use the second eigenvalue, and again, we look at a minus r times I times the vector of unknowns equals 0. The matrix we get in this case, subtracting r from the diagonals, so subtracting 2 from the diagonals, is as follows: 4, minus 4, and 3 this time. With this matrix, it's a little less obvious than it might be in other scenarios, but these two are the same thing, just multiplied by negative 1. So the real interesting rows are the first and third rows. So what we're going to do now is do some row operations to simplify this and make it easier to work with. But what we're going to do is eliminate one of the rows off the bat. So keep the first row. Why not? We have to keep one of the first two. We'll take the first and the second row. They'll give us all zeros. And then we'll take the third row and the first row, and we'll do 4 times the first, and we will add the third row. That'll give us negative 4 plus 4, which will give us a nice leading 0 out front. The other terms that we get are going to be 4 times this is 8, plus minus 4 is going to be positive 4. 4 times this is negative 4, plus 3 is negative 1. All of that times v1, v2, v3 equals 0. And so we can copy those out. We'll take the second row first. 4v2 minus v3 is equal to 0. So 4v2s equals v3. So v2 is equal to 1/4 of v3. We get to pick a value. We'll pick it so it's a nice integer. Not just v3, but also v2, so we'll pick v3 to be 4. and that will immediately give us that v2 is going to be positive 1. Then we can go to our first equation here and say that minus v1 plus 2 v2s minus v3 has to equal 0. We know these values now. This is 1, this is 4. We'll bring the v1 over to get the sign cleared up, and this is 2 minus 4 is negative 2. And so this time our vector v2, which is equal to our first component, negative 2, our second component, which is 1, third component, 4, is the eigenvector corresponding to the eigenvalue, which is 2. Last but not least, we have our third eigenvalue, and we're going to find its eigenvector as well. So again, we're doing a minus r times I times a vector equals 0, and that we're going to compute with r equals 3. So we'll have 1 minus 3 is negative 2. The other elements are the same. Then we put down the diagonal, the minus 3's, 1, 4, negative 4, and 2. All that times v1, v2, v3 equals the 0 vector. We see once again that requirement that one row is redundant. We need that if we've gotten the correct eigenvalue. And we see that here just by the first row and the third row being related by a multiple of negative 2. That means we can go ahead to row reduce. And when we do that, we can just keep the first row. It has a nice simple coefficient out front. We get the last row, which would be the first and third combined. And for the second row, what we're going to do, again, it's totally up to you, but the choice that makes sense here, I think, is to take the first row minus or plus 2 times the second row. That'll give us negative 2 plus 2, which gives us 0. Then we'll have this plus 2 times this, so 2 minus 6 is minus 4. Then negative 1 plus 2 of these is a positive 1. And that gives us a relationship between v1, v2, and v3 that's easier to work with. Let's take the second equation here to start with because it's simpler. And that second equation gives us negative 4 v2s plus a v3 equals 0. So v2 is 1/4 of v3. We want nice integers if we can get them, so we'll pick v3 to be 4. And that will immediately give us v2 is 1/4 of that, or just 1. Then we can go back to our first equation, and that first equation tells us that v1 minus 3 v2s plus a v3 is equal to 0. We have the values for all of these, and so v1 equals minus 3 plus 4 is 1. It's going to be negative 1 when we bring it to the other side. And so v3 as a vector is first component negative 1, second component 1, third component 4 is the eigenvector we're looking for now. And it's corresponding to the third eigenvalue, which was 3. Yes, a chunk of work, but on the plus side, all this work here is automatable. This computing of eigenvalues and eigenvectors is straightforward with computer software. What's interesting for our perspective is constructing the general solution. So our general solution is C1 e to the first eigenvalue t times the first eigenvector, which if you look back in your notes is negative 1, 1, 2, plus C2 e to the 2t times the second eigenvector, which is negative 2, 1, 4, and the third eigenvector and value pair is e to the 3t, and we have it right here, negative 1, 1, 4. And that is our general solution. So we just have one last step for this example. Remember, we were told what the starting value was, and we're going to use that information to solve for C1, C2, and C3. Let's play that out. So what we're going to do is use the initial condition to solve for C1 and C2 and C3. The nice thing about this is the initial condition is at time equals 0. And we remind ourselves that e to the 0 is just 1. So it actually disappears in all of our equations right off the bat. So what we can do is simply write our target. We want the starting value to be -1, 0, 0, and that's going to be just a linear combination of the vectors that we have found before. So we just need to hunt for these three coefficients. And again, any way that you want to do this is fine. I think the easiest way to do it is, again, to put it in a matrix form. And the way we can do that is we think of this column times C1. So that would be -1, 1, 2 times C1. And then the next column, -2, 1, 4 times C2. So we're building a vector on the right here. And then -1, 1, 4. All of that gives us -1, 0, 0. And then we can do row reduction, with the only wrinkle that's new here is that we have to do the same row operations on the right-hand side as we do on the left-hand side. Previously in this example we had 0 values, so adding zeros and multiples of zeros never changed anything. To start, we'd like to get some nice leading zeros off the top, so we can take 1 and 2. We'll leave 2 as the top one because it's just so nice and simple. 1, 1, and 1. For the next one, we'll take 1 plus 2, and this is going to be 0, -1, and 0. Fantastic. Then why don't we take the first times 2 plus the third. 2 times the first plus the third. That gives us 0 as the leading coefficient up front. 2 times this plus this is 0. 2 times this plus this is -2. And then we have to do the same thing on the right-hand side. So we take the second coefficient, we take the first plus the second, that's -1. We take 2 times the first plus the third, that's -2. And that lets us read off 2 of the values immediately. We have -2C3 is -2, so guess what? C3 is 1. And we have -C2 is -1, so C2 is 1. And last but not least, C1 plus C2 plus C3, this first equation has to add up to 0. These two values are both 1s, so that's going to give us C1 is -2. So if we took these and put them back in here, we would get our particular solution. We've spent long enough on this problem already though, so I'll copy this to the next page, but we'll stop the video here.